Good afternoon, everyone. I am Thomas Vitalis, PhD candidate at UMass, and I will be talking about improving the confinement of concrete structural members with auxetic steel truss lattices as a reinforcement. So I will briefly introduce the motivation of the study, then talk a little bit about reinforcing phase architectural selection. Then talk about the manufacturing and characterization of the reinforcing phase, and end with the fabrication and the mechanical properties of interpenetrating cementitious phase composites. So this study is primarily motivated by architected materials, and specifically auxetic truss lattices. So auxetics are a special family of truss lattice materials which have negative Poisson's ratio. So that basically means that when you apply a compressive load to an auxetic truss lattice, it deforms laterally inwards instead of expanding as a normal positive Poisson's ratio material would do. This happens because of the specialized design of the interior angles, which are usually sharp re-entrant angles, and this can benefit composite material with a cementitious matrix. So in this work, we are trying to study the confinement increase that a concrete structural member would have, such as a column, for example, right? If we embed a material, an auxetic truss lattice material, inside a composite matrix using a mortar or concrete. Such as we would have in a typical column. So we all know that these columns have lateral hoops that prevent the expansion of the effectively confined core, and this essentially boosts the performance of the confined concrete columns. So to initiate this study, we selected two architectures from the literature. These are the two architectures. We have the double pyramid architecture and the bow tie architecture. These were three-dimensional truss lattice architectures from the literature, and we selected these two because of the degree of the openness of their unit cells and the relatively low nodal connectivity that allowed us to manufacture experimental specimens that can effectively be compacted when a cementitious matrix can enter them. So first, we wanted to quantify the confining pressure that these different architectures can exhibit upon a cementitious matrix. To do so, we started by performing a solid element, finite element analysis using RV homogenization methods, and we calculated a variety of different unit cells using periodic boundary conditions, and then using the finite element results, we decomposed these calculations using a Voigt model to estimate the properties of the compliance tensors of the two phases. And these phases, the matrix is assumed to be isotropic, and the lattices that we have here with tetragonal unit cells are orthotropic. So using this, we were able to calculate the increasing confining pressure percentage-wise using this confining scheme. So we have hundreds of different unit cells with different characteristic angles, which are these angles. And in the case of the double pyramid, we have two angles here in this family. And out of this, we calculate the increasing confining pressure that the truss lattice can exhibit upon the concrete matrix. In this case, we expect to have a passive component that comes from the expansion of the concrete matrix itself, and we also expect to have an auxetic component that comes from the strain mismatch of the truss lattice moving inwards towards the concrete matrix. So from this study, we found these results for the Poisson's ratio and the transverse moduli, and the axial moduli and the transverse moduli here for a variety of different architectures with different characteristic angles. And we selected 6 architectures. We selected these 3 for the double pyramid architectures, and these 3 for the bow tie architectures. So this selection happened based on the increase in confining pressure upon the matrix, and also we want to select architectures that exhibited a variety of transverse moduli to also explore the compliance of the truss lattices exhibited upon the matrix. So these are the architectures we selected, 3 and 3, for these 2 families. And using these architectures, we made tessellations. We wanted these tessellations for our experiments, and we made them as close as possible to cubic, using dimensions close to 2 by 2 by 2 inches that come close to the ASTM C109, which is used to characterize mortar specimens, which we use for the matrix phase in the study. And we manufactured these architectures using laser powder bed fusion and using stainless steel metal powder. And we also performed material characterization here for this. I won't go into much detail, but we did some work using SEM and micro-CT to see potentially perfection in the S-built parts and also to characterize the anisotropy of the built parts. So I want to focus on this stress-strain relationship of the bare trusses. This is the test we did only for the reinforcing phase of the composite, and we tested these under axial compression, and we see the results for both the bow tie architecture that I'm showing here. So we have these 3 different re-entrant angles, and for the double pyramid architecture, we also have these specimens here. We have observed different axial moduli that agree with the previous computational work, and also we see different peak stresses with the 85-degree angle performing the best, followed by the 80-degree angle, and followed by the 75-degree angle. And for the double pyramids, we observe significantly better peak stresses for all of the specimens, and also we see a much stiffer behavior for these truss lattices. And of course, after these experiments, we have additional measurements, additional metrics for the energy absorption of these truss lattices. We calculated the angle change up to the peak load, and using the simulation results, we were also able to calculate the properties of this truss lattice, this finite-sized truss lattice tessellation at different relative densities. So all of this work was preliminary work for us to understand the reinforcing phase of the composite, so we could move forward and manufacture these cementitious interpenetrating phase composites for concrete and mortar, essentially. So we started with a mortar optimization using the same exact architectures but made out of nylon, which is more cost effective, and we could do more runs and test more the mortar phase, which is the soft phase in this matrix. And after doing so, we did several iterations of different mortar mix designs, which were based on the ASTM C109 with some slight modifications to make it more flowable and able to penetrate these dense structures. And we were also interested in seeing if there are any voids in the composites, which we were able eventually to remove the voids from these composites. And after we did this preliminary work, we were able to cast the stainless steel truss lattice specimens, cure them for 28 days, and test them under axial compression on the 28th day. And before moving to the IPC results, I want to show you first some of the properties of the plane matrix phase. First, we did some ASTM tests to quantify the mechanical properties of the mortar matrix before we moved into to the composites. So here in this slide, I'm showing the results of the cementitious interpenetrating phase composites. On the top, I have the bow tie architecture, so I have the 75, 80, and 85 degree specimens. And on the bottom, I have the double pyramid architectures using this 1545 degree, 1560, and 3048 here. And again, these come from the preliminary explorative finite element study. And for each specimen, we have 3 repetitions. So we did 3 repetitions of each test. And we were also able to get good agreement with computational simulations. So here with the green lines, you will see the simulations we have for these composites. First thing that needs to be said here about this is that the bow tie architectures succeed in reinforcing the concrete phase very well. We actually get an increase from 40 MPa, that is the peak stresses for the cementitious matrix on average. We get an increase of up to 140, 150 MPa here for these bow tie architectures, along with an increase in ductility. And for the double pyramid architectures, we get an increase of up to almost 80 MPa here, and a little more for the 3048. So these double pyramids also succeed in reinforcing the soft matrix phase. However, they don't perform as nearly as well as the bow tie architectures. And once we did this, we were curious about how a conventional reinforcing scheme that is used for confining concrete, such as the ones I showed in the previous early slides, would look like if we tested them and compared them with these. So we used the same unified model that we used for the interpenetrating phase composites, and we also modeled these conventional confining schemes, these architectures using different schemes of hoops here to confine the concrete core in these cases. And these are the results of these calculations. And these simulations have shown that the failure modes that dominate this behavior are basically the snapping of this intermediate hook in between the midspan of the specimen. In every case, once this hoop fractures, then we have an immediate loss of capacity and essentially the failure of the specimen in the case of the of these conventional reinforcing schemes. So this is something that we don't see in the IPCs due to the redundancy from having multiple struts in the architectures. So in this slide, I have a comparison of all the reinforcing schemes that we have studied so far. And we have the bow ties here shown with the blue lines on the top that perform extremely well. Then we have the conventional reinforcing schemes that we have, we just saw a minute ago in the previous slide, and also the double pyramid architectures that somewhat succeed in reinforcing the concrete matrix. However, they don't perform as well as the bow ties or even the conventional ones. And the unconfined specimen stands here at around 40 MPa again. So from this work, we have observed a peak ductility increase of 240% compared to the conventional, so going from the green line to the blue line, and an increase in the peak stresses of 65%. And this behavior of the bow tie architectures compared to the double pyramids and the conventional reinforcing scheme is also explained using the Poisson's ratio or the dilation ratio in different strain progressions, which essentially means that the bow tie architecture succeeds in bringing down the effective Poisson's ratio. So we are lowering the effective Poisson's ratio of the composite, and we are also having a better performance in the nonlinear region through strain progression compared to the double pyramid architecture and the conventional one. So some future directions for this work that we're currently working in the lab are the analytical modeling of this work. So essentially we want to model concrete column prototypes that have similar dimensions to the ones, to the columns that we can see in construction. And we have prototyped these, and we're going to test them and make an analytical plasticity model, such as the ones that are studied by Mander and Attard and Foster and other researchers throughout the years. And We are also working on upscaling this work using robotics, so using robotic assembly and also robotic welding. And this is one preliminary specimen that we made using this process. And we're also using 3D scanning to assess the quality of this fabrication process. So with that, I will conclude the presentation with the following results that we found out from this study, which are the following. We have succeeded so far in harnessing the strain mismatch between the two composite phases that gave us unprecedented energy absorption, ductility, and strength under axial compression. We have observed increases in the compressive strength of 65% in terms of strength and 140% in terms of ductility inside the IPCs when compared to the conventional reinforcing schemes or confinement schemes. We have also observed the transition from the bending-dominated architectures that are the truss lattice phases alone, which then transitions to stretching-dominated behavior inside the IPCs, which also leads to an increase in the hydrostatic pressure of the truss lattice, and that essentially let us squeeze every last drop of strength that the lattice can give to the IPC. We also observed a non-rule of mixtures mechanical response inside the IPCs, which was quite interesting in this case. And as a final thought, we can create a balance between stiffness and energy absorption to engineer materials that respond to a certain demand for different engineering purposes. And with this, I will conclude the presentation and hear your questions. Thank you.